Hello everyone, welcome to the lecture of digital signal processing, the first lecture. In this we'll be learning the introduction to digital signal processing. The contents of this particular lecture will be introduction to digital signal processing, very basic, why we go for digital instead of analog, and why frequency domain is preferred rather than using time domain signal as it is for signal processing. And lastly, we will revise DTFT, which is basic building block for DFT, which is used in a digital signal processing. So without wasting a time, we'll start our module. As we all know, though DSP is not a maths class, we'll have some simple mathematics for understanding the concepts that will include some finite and infinite standard summation series and some finite integrals and some derivations, simple derivations we'll see when we come across. We'll see why we go for digital signal processing rather than using analog. Digital computers cannot handle continuous and long data. As we all know, signal processing techniques in digital domain has very powerful tools and ability to generate results which otherwise won't be possible if we use analog signal processing. Even an extreme difficult analog signal processing, a complex one, it's not possible to get similar results. So obvious choice is the digital signal processing. Some examples are FIR filters with linear phase, adaptive filters. Also, in analog circuits, the analog components used such as resistors, capacitors and inductors, they does not behave same in all working conditions. Their inherent tolerances, temperature dependency, voltage changes and mechanical vibrations may deteriorate their stability and their performance. And hence, the effectiveness of the designed circuit will not be as good as that in a digital domain circuit. Also, in a digital signal processing, we generally have a piece of code or an algorithm. If we want, we can change that complete code easily. Unlike in analog domain, we have to change physical components. Here we can change the piece of code easily. We can correct it at some points. We find something is wrong, we can correct it, or sometimes we at later stage we can modify it if we want to modify our complete process. So this all can be done in no time with no cost involved and very easily compared to analog domain. The additional advantages are noise susceptibility, chip count, development time, cost and power consumption, obvious. So because of these all reasons we go for digital signal processing. And the obvious disadvantages that we have in a digital signal processing are only two disadvantages. Those are the ADC compatibility when we go for fast processing and a complex design when compared to that in a real-time processing. Now we'll come across another topic in this first module, why we use frequency domain rather than using time domain. To explain this, I will use a simple graph, sine wave graph. As you can see here, this is a 1 Hertz graph and corresponding frequency spectrum is also shown below it. This is a graph, it's 1 Hertz frequency spectrum. Now if I apply this graph as this sine wave as an input to the system, this system is simply a buffer which takes input and produces output as it is. It does not alter our input. So unfortunately there will be some noise which is present always everywhere. So output produced by this system will not be exactly same as the input sine wave. It will be something like this, the deteriorated waveform, the distorted waveform. And we cannot easily identify the time domain nature of the corrupting noise. The noise which corrupts this signal cannot be identified in a time domain because this happens for all time instances from t equal to minus infinity to t equal to plus infinity, and we cannot easily identify time nature of a signal for that lengthy period. What if we have a frequency domain nature of that output signal like this? What does it tell me is this has a frequency content at 1 Hertz and some other frequency is present which probably might be the frequency of that noise signal, in case if that noise has a specific frequency which is not spread over a whole frequency range. I am assuming this. So if that noise is for specific frequency, then in frequency spectrum we can identify that culprit and we can remove it by using some filter which will pass this frequency and block this frequency. So my task became easier when I used frequency instead of time domain. Similarly, analysis becomes easier in a frequency domain. If you remember, if you have learned any transform, you might have seen that the time domain convolution is equivalent to frequency domain multiplication. So this is the reason analysis becomes easier. Simple product in a frequency domain and then take inverse transform, you get a result same as a convolution result. So because of these obvious reasons we go for frequency domain processing. Now in digital signal processing we will be using discrete Fourier transform, which is none of these 4 analysis methods being shown here. DFT is derived from this DTFT. And why these 4 are not suitable for digital signal processing, we'll see that. Though we will not go in detail of DTFT, but we'll just understand what it is in DFT point of view. How it is derived, what is relationship between DTFT and DFT, we'll learn only that much. Okay. So to understand this graph, you can pause this video for some time, you can have a closer look at each of these categories and then you can come back. So you see a continuous time Fourier series, a continuous time Fourier transform, discrete time Fourier series and discrete time Fourier transform. Now if we want to understand the nature of signal in different domains, time domain and frequency domain, for all those different Fourier analysis methods, we will have to remember this table. It might be confusing to remember a complete table, so we'll see some tricks and we'll try to relate some things which will make it easier for us to understand and remember. So the term CTFS means continuous time Fourier series, CTFT continuous time Fourier transform, discrete time Fourier series and discrete time Fourier transform. The name itself suggests that the first 2 letters tells us the time domain nature of a signal. It is continuous time, this is continuous time, this is discrete time as you can see here, this is discrete time you can see here. Okay. When we use a transformation Fourier series, it is generally best suited for periodic signals. When we use Fourier transform, it is best suited for a periodic signal. It does not mean Fourier transform cannot be used for periodic signal. It's not like that. It can be used for periodic signals, but it is better to use it for a periodic signal, which will simplify our task. So with that logic, we see that when we compute Fourier series, the time domain signal is periodic. When we compute Fourier series, time domain signal is periodic. When we compute Fourier transform, time domain signal is aperiodic. Here also. So it became easier to remember this first row for all 4 columns by using this label itself, CTDT or Fourier series Fourier transform. For remaining, we have to remember these first 2 things. We know that for continuous time Fourier series, if you remember trigonometric Fourier series, we compute coefficients n, bn. For compact trigonometric Fourier series, we compute coefficient cn. These all coefficients depend on value n equal to 0, n equal to 1, n equal to 2, n equal to 3, and so on. That means those are discrete coefficients. So Fourier series, in a continuous time Fourier series, gives us a discrete coefficients, and all those are aperiodic in nature. A0, A1, A2 all are unique values, they are not periodically repeated. So the continuous time Fourier series is a discrete and aperiodic. Continuous time Fourier transform, if you remember capital X of omega, we obtained a single aperiodic continuous spectrum. So it is continuous and aperiodic. If you remember these two, it will be easier for you to remember rest. How? That I will tell you. For that, you look at the second point. It's very important. When a time domain signal is sampled, then its corresponding frequency domain spectrum will be periodically repeated. And this is vice versa. What I mean to say is, if frequency domain spectrum is sampled, then corresponding time domain signal will be periodically repeated. And if you remember this thing, it will be easier for you to remember these last two things. So see, continuous time Fourier series, discrete time Fourier series. In both of these, time domain nature is periodic. Only continuous is sampled to make a discrete. So when continuous is sampled and made a discrete, corresponding frequency domain will become periodic in nature, as I explained in this statement. So here this aperiodic becomes periodic. Rest of the nature is discrete, discrete as it is. Similarly, here continuous spectrum is sampled to make a discrete. Remaining thing is aperiodic, aperiodic as it is. So when continuous is made discrete, aperiodic becomes periodic, and vice versa. So these are the different transforms. Now in discrete time Fourier transform, as we saw in a previous explanation, we have capital X of e raised to j omega is equal to some, as it is used for aperiodic signals which ranges from n equal to minus infinity to n equal to plus infinity. As it is used for discrete time, we will have summation, because discrete samples are to be summed up by multiplying with e raised to minus j omega n. This is a definition of direct Fourier transform. This is also called as an analysis equation of a Fourier transform in a discrete domain. And small x of n is equal to 1 upon 2 pi integration minus pi to pi capital X of e raised to j omega e raised to plus j omega n d omega. This is called as an inverse discrete time Fourier transform, or it is also called as a synthesis equation. How to remember this? You know that x of n is a discrete time aperiodic signal. Its discrete time Fourier transform is periodic with period minus pi to plus pi, because minus pi to plus pi is a unique range in a digital frequency domain. After that everything gets repeated. So x of e raised to j omega is a periodic and continuous function of frequency. So as it is a continuous function, we need to integrate it instead of using a summation sign. And as it is extended from minus pi to plus pi uniquely, we will be using minus pi to plus pi. And this is a scaling factor 1 upon 2 pi, which obviously comes. For that we have to see a derivation, which I am skipping here. So we have an inverse discrete time Fourier transform equation, and obviously if we take modulus on this, we have to take individual modulus on this, and that quantity will be always larger because we are performing individual modulus. So this thing modulus is less than equal to summation individual modulus of this and this. So that I have written here. And modulus of e raised to minus j omega n, it is a sinusoid, complex sinusoid. So its magnitude will be always equal to 1. So as I know, I have represented here, its magnitude is equal to 1, and because of that this quantity, this whole quantity can be represented as only this. So if discrete time Fourier transform needs to be exist, that means if this exists, then obviously the right side will be less than infinity. So for existence, this is a condition. In a statement, I can say DTFT exists if x of n is absolutely summable, meaning summation over minus infinity to infinity of x of n needs to be some finite value. We'll see and revise some properties of discrete time Fourier transform which have been already studied in a semester 6th. So first obvious property is linearity. We know that DTFT is simply a summation over signal into e raised to minus j omega n. So that summation is distributive over summation. So that summation, if I take this as a whole signal and if I find DTFT of this, it's equal to finding DTFT of this plus DTFT of this, because distributive over this plus. So I have a into x of e raised to j omega plus b into y of e raised to j omega, where a and b are some constants which can be taken outside of a summation sign. So this is obvious linearity property. We can easily operate DTFT over individual terms when different signals are linearly combined. Time and frequency shift property. When input signal x of n is delayed by some time amount d, its corresponding frequency domain signal x of e raised to j omega will get multiplied with e raised to minus j omega d. Remember, this is same as an operator used in a DTFT. The only difference is n is replaced by specific shift amount, that is d. And similarly in frequency domain, if capital X of e raised to j omega, now frequency is shifted by omega 0 amount, that gives you this thing. Then in corresponding time domain, we have an operator with plus j omega 0 n, and here omega is replaced by omega 0. To remember, once again you can have a look here. This is a frequency domain data. So in this frequency domain data, nowhere we can have term n. So that's why there is no n, but there is d. What is d? D is a specific time shift which is not a variable, some number, specific number. Similarly, this is a frequency shift and corresponding time domain. As it is a time domain, here we cannot have a frequency variable. So omega is replaced and instead omega 0 is used. What is that? That is a frequency shift amount, and that is a specific frequency value. It is not a variable omega. Third property is time reversal property. When we perform time reversal of a time domain signal, corresponding frequency domain also gets frequency reversed, and very obvious. Then differentiation property says that n x of n, multiplication of x of n with a time index n will produce j into d omega of x of e raised to j omega. Differentiation. As I said, in most of the not almost all transforms, convolution in time domain is equivalent to multiplication in a frequency domain. Obvious. The similar property dual of this is convolution in a frequency domain. This is called as a periodic convolution. Why? Because that frequency spectrum is periodic in nature. So this is periodic convolution that is equivalent to time domain multiplication. So time convolution is frequency multiplication and time multiplication is frequency convolution. And at the end, the Parseval's theorem, which says that the energy of a signal x of n in a time domain is equal to 1 upon 2 pi into area under the squared magnitude of capital X of e raised to j omega. Okay, you have to remember this because we are not proving this all as we are revising DTFT. Some more properties of DTFT are symmetry properties. You can pause this video at this moment and you can have a look at these properties. What does it say? When signal is even or symmetric, its corresponding spectrum is also symmetric. When time domain signal is anti-symmetric, spectrum is also anti-symmetric. And when time domain signal is real, the frequency domain spectrum is Hermitian symmetric. We'll understand a simple example of DTFT just for a revision, and then I will relate DTFT with DFT in the next lecture. Here we have a simple low pass filter. Why low pass filter? Because as I said, digital frequency is extended uniquely over a range minus pi to plus pi, and in that range this is passing frequency from 0 to omega c, and it is blocking frequency from omega c to pi, and that's why it is called as a low pass filter. Low frequency is passed, high frequency is blocked. Okay, and you can see the analytical equation also. H low pass of e raised to j omega, this is just an abbreviation used for understanding, is 1 over frequency less than omega c, and response is 0 for frequency above omega c up to pi. So if we want to find the time domain nature of this low pass filter, we will have to use IDTFT equation, that is this IDTFT. Here we have h low pass of n is equal to 1 upon 2 pi integration over minus pi to pi h low pass of e raised to j omega into e raised to plus j omega n into d omega as usual. If we substitute value of h low pass of e raised to j omega here, and we look at the actual range where that signal is present, we can modify this formula, because signal is present over minus omega c to plus omega c, and actual value is 1 into e raised to j omega n d omega. We straightforward solve this. E raised to j omega n is integration e raised to j omega n upon, with respect to omega, so upon nj, then e raised to j omega n integrated from minus omega c to plus omega c. The integration will look something like this. We can convert it to e raised to j theta minus e raised to minus j theta divided by 2j, a sinusoid identity, sin theta, and divided by n pi as it is. So this looks like a sinc function. H low pass of n is a sinc function. So in the next slide, I have written an equation for a frequency domain filter and an equation for a time domain signal obtained for that ideal filter. So you see that it is a sinc pulse. Now we'll see how we transform from DTFT to DFT. Before we go in depth of DFT, we'll see the relationship between DTFT and DFT. As you can see here, the first graph on the top is a pair of continuous time Fourier transform. We'll have a quick understanding of this whole. This is continuous time Fourier transform. The continuous aperiodic signal produces continuous aperiodic spectrum. If I periodically repeat this in a time domain, corresponding spectrum will get sampled with the logic that we understood in a previous slide. So this is periodically repeated, this will be sampled, and this makes a continuous periodic time domain and discrete aperiodic frequency domain, and that is actually a continuous time Fourier series. This is CTFS, continuous time Fourier series. Now third graph is a pair of discrete aperiodic signal and its corresponding continuous periodic spectrum. This is discrete time Fourier transform. If I periodically repeat this thing down, then this will get sampled, and this is discrete periodic, this is also discrete periodic. And what is this? This is a pair of discrete time Fourier series. Discrete time Fourier series. So if I have aperiodic data like this, which is to be processed by using digital computer, then its corresponding frequency domain will be continuous in nature. So it cannot be processed. The continuous data cannot be processed using digital computer. So what we can do, we can sample this DTFT and we can obtain something like this. So we want, this is given data, discrete, aperiodic data, and we want its frequency also to be discrete. So we want this, and this becomes a new pair of a transform that is called as a DFT, discrete Fourier transform. We will see how DFT is different than DTFS in next lecture.